Welcome to the Explainer. Listen, if you've been building with AI recently, you already know the game has completely changed. Today, we're moving way past basic prompting. We are going to unpack exactly how to build battle-tested systems that can actually survive the absolute chaos of real-world production.
So here is the billion-dollar question we need to answer right out of the gate. Why do AI agents completely fall apart the second they hit production traffic? Because we've all been there, right? Your agent works beautifully on your local machine, gives you the exact perfect answer, but the moment you deploy it and real users get their hands on it, it crashes, it hallucinates, or it just gets stuck in this endless spinning loop. And here's the tricky part. AI crashes differently than traditional code. You don't get a nice clean stack trace. Instead, it fails silently by outputting incredibly confident, articulate nonsense. We have to fix that. Okay, here's our roadmap for building a deterministic architecture today. We're going to cover the paradigm shift, the anatomy of an agentic loop, harness engineering, stopping conditions and budgets, and finally verification with the Mint framework. Let's dive in.
Section 1. The paradigm shift. Let's quickly look at how AI engineering is evolving and why chasing the perfect prompt is basically old news.
Think about the evolution we've seen here. Just a couple of years ago, the highest leverage skill you could have was prompt engineering, literally agonizing over specific words because the models were just so rigid. Then, as models got better, we shifted into context engineering, where the whole focus was curating exactly what data landed inside the model's context window. But right now, we're firmly in the third era, loop engineering. Because modern models can write their own prompts and pull their own context using tools, the scarce skill isn't the input anymore. The scarce skill is designing the cycle itself.
So the crucial takeaway here is that loop engineering is the actual, practical, technical discipline of how production AI systems are being built today. Instead of handwriting every single step of a process, you're designing a robust cycle: act, observe, verify, and retry. What happens between the steps? When does the agent pause to check its own work? What is the exact self-correction mechanism when a step fails? That is loop engineering. Moving on to Section 2, Anatomy of an Agentic Loop. Let's break down this foundational primitive.
Let's make this concrete. Imagine an AI customer support agent handling refunds. Using the React pattern, which is reason, act, observe, repeat, the model reasons about an incoming message, decides on a tool action, observes the result, and loops right back. So, in iteration 1, it classifies the intent. Okay, this is a refund request. In iteration 2, it realizes it needs order details, so it calls the order lookup tool. The observation comes back, and in iteration 3, it checks that specific data against the company refund policy. Finally, in iteration 4, it drafts a reply. Every single one of those steps is a pass through the exact same fundamental loop.
Section 3. Harness engineering. This is where we get into the deterministic guardrails.
Harness engineering is essentially traditional software development applied to AI. It's funny, people get so mesmerized by the creative, non-deterministic magic of the AI model that they completely forget a production agent is still, at its core, traditional software. The harness is the deterministic code wrapped tightly around the model. To actually survive production, you absolutely need the 5 essential loops: retry logic for when API calls inevitably drop, validation to check data shapes, fallback chains for when the model hallucinates, human-in-the-loop for necessary escalations, and strict monitoring. Without these 5 loops, your AI is just going to fail silently. Get this, it's a stark, almost surprising contrast, but the model itself, it might only be about 5% of the actual magic in your system. The other 95% is that boring deterministic scaffolding ensuring it survives real-world traffic. The engineering teams that are successfully shipping reliable agents treat this harness just as seriously as the AI model itself. You aren't just evaluating if one AI reply sounded good, you're evaluating if the entire system degrades gracefully when an external API goes down.
Section 4. Stopping conditions and context budgets.
You really have to understand the economics here. Latency and cost scale directly with loop length. If you have an agent that takes 10 steps to complete a simple 2-step task, that is a massive 10x multiplier on your inference bill. A runaway loop isn't just a slow, annoying user experience, it is an absolute budget destroyer. This is exactly why minimizing unnecessary iterations is a core part of your cost runaway protection.
Because you simply cannot fully trust the model's own internal sense of being finished, you must deliberately design stopping conditions, what we call agent loop traps. You need explicit termination signals, like hard iteration caps and strict token budgets. This is exactly where you implement the circuit breaker pattern. Think of it like this. It's closed when the loop runs normally, open to immediately kill the loop if it hits a cost threshold or errors out repeatedly, and half open to gently test if the external service is recovered. These act as your essential failsafes.
But wait, there is another hidden danger lurking as your loop runs: context rot. As the loop iterates, every single tool result and intermediate reasoning step piles up in the context window. Long before you ever hit the hard token limit, the model starts getting measurably worse because its window is just filled with stale, low-signal tokens. This is the exact reason why long-running agents often start out super strong and then completely lose the plot and start hallucinating halfway through a task.
So, to fight context rot, you have to actively budget what gets to stay in that window. You can use compaction, which means periodically summarizing earlier steps so the model keeps the thread without dragging thousands of raw tokens around. You can use external memory to write facts out and only retrieve them when actually needed. And, critically, tool result management. Please do not just dump 1,000 rows of a raw database query into the prompt. Filter it and extract the data first. Funnily enough, spinning off a complex multi-agent system is quite often just a glorified context management strategy to keep your main loop lean and focused.
Finally, Section 5, Verification and the Mint Framework. Let's look at building that production-ready stack pipeline. There is a really foundational design rule here for verification. Some outputs are cheap and highly reliable to verify automatically, like checking if generated code compiles, or checking a hard rule that any refund over $100 has to escalate. Other outputs are wildly subjective, like judging if a refund decision was truly reasonable given a customer's unique, messy backstory. The rule is simple. Automated, cheap verifiers belong firmly inside the loop for instant self-correction, but whenever a task is genuinely subjective, that dictates exactly where a human-in-the-loop must step in.
So how do you build all this without completely losing your mind? You use the minimal intelligence necessary tools, or the MINT framework. You have to build incrementally. Start with a basic prompt end-to-end, then add tool use, then add continuous evaluation, then state and memory. Only at the very, very end do you add complex multi-agent orchestration. At every single layer, you have to stop and ask, how does this break? Rather than just bolting on 3 vector databases and 5 subagents on day 1 and wondering why the whole system is failing silently.
Zooming out a bit, AI pioneer Andrew Ng describes building software as 3 nested loops. You've got the fast agentic coding loop running in seconds to test implementation. Then, the developer feedback loop, where you, the human, review and update specs over minutes or hours. And finally, the external feedback loop, run by the real world over weeks. Notice the trend? The further out you go, the more verification completely depends on human judgment rather than automated tests.
Ng's 4 original agentic design patterns are actually perfectly represented in our support agent pipeline from earlier, proving these aren't just abstract academic theories, they are the literal building blocks of your loop. Reflection is the agent checking its own draft. Tool use is the order lookup. Planning is sequencing the classification and response. And multi-agent collaboration handles those specialized subtasks to keep the main context perfectly clean.
I'll leave you with this final provocative challenge to think about. Are you currently evaluating a single perfect AI sentence, or are you actually building a battle-tested system under stress? Because if your model starts hallucinating, or an external API drops offline right this second, does your system gracefully recover, or does it silently pass a catastrophic failure straight to your user? It's time to stop polishing one node and start engineering the loop. Thanks for hanging out with me for this explainer. I'll catch you next time.